this variation in current, I'm going to speed up the speed of the rotation. And finally, if I go really fast, then I am going to create even faster RPM as I fluctuate the current. So that is an alternating current. I've actually produced an alternating current there. And if we go to the next slide, the rotational speed of that bar magnet in the middle depends on the frequency of the alternating current. So if I have a low frequency alternating current, I'm going to get a relatively low RPM. If I have a high frequency, frequency current, I'm going to get a higher RPM. And that's exactly the way a variable frequency drive works. Now, as we all know, this is a three-phase motor, and we're using three-phase power. So we don't just only have the A phase. We also have a winding for the B phase and a winding for the C phase. And if we remember, all those phases, that pulsation, that sinusoidal wave is 120 degrees out of phase. So what we get is, when we are at the peak of our A phase, we get those magnets at the A and the B the strongest, and they are going to repel the inner rotor. Then as it comes around to the B phase becomes the largest current, and therefore the B magnets become the strongest, and it repels the rotor once again. And finally, this poor rotor doesn't know what to do. It just it's chasing its tail, and it starts the rotation process. So let's get these oscilloscopes going here. Let's feed this with three-phase power, these three circuits that we have here. And essentially what we're doing is we're inducing this rotating magnetic field. That's the outer core, that outer colorful pattern. And that's constantly rotating around. And this poor rotor in the middle, or this bar magnet, is chasing itself. And we're getting motion. I've lied to you a little bit to make it simple, but now I'm going to get a little more complicated. This, in a three-phase AC induction motor, is not a fixed magnet. What it really is a rotor, and it's not a magnet at all. It becomes a magnet, but it's not a magnet by definition. So what we have here is on the right side, we have a rotor, and inside that green housing are all these windings, these circuits that we were talking about, and in the middle is a rotor. So let's pull out that rotor. And we're going to put it inside of the windings, but we want to take a look at those windings. So if you remember, we had the A winding, two A windings, two B windings, and two C windings. And that rotor actually looks like a squirrel cage. And I think many of you have probably heard squirrel cage motors. This is why it's called squirrel cage type of motor, because it has these bars that go from one side to the other. And these bars are filled, and you can see them right here, are filled with some kind of metal plates that give it inertia once it starts to turn. And if you remember here, the C, A, and B at the top here, they are all in one phase, or one induction type. We're in the north or south, whatever the red was. And at the bottom, we're in the opposite, the north or south, always the opposite. And what we're going to do is we are going to induce a current in those bars of that rotor. So remember, when we run a current through a coil, we get a magnetic field. When we run a magnetic field nearby a bar or a piece of metal, we get a current. And those currents are the strongest at the very top and at the very bottom, in this case anyway. And as we come around, they get smaller and smaller. And finally, they reverse as they come around to the blue A. So we're getting a change in current. And that induces, this change in current induces its own magnetic fields. And guess what that looks like? It looks like that bar magnet that we had to begin with. So we're essentially, by running electricity through the stator, we're actually turning this rotor into a magnet. And that's great, because now everything that we spoke about still is going to hold true. So let's go now to what these windings actually look like. So there's three windings, one for each phase, in this case anyway, and these all get put together and they get put inside of a stator. And they get put inside evenly, and it's looks kind of messy when you've opened one up, but it is pretty precise. And then inside, we have the rotor, real close to the influence of those magnetic fields that are being induced by the electric fields. And essentially, if you were to open this up, you would see not just 3 big wires, you would see all these windings, these very small wires where the current is going through, inducing that magnetic field. Now, let's get to variable frequency drives. So what did we say before? If we vary the fluctuation of that AC current, then we will vary the way that those magnetic fields on the outside on that stator fluctuate. So therefore, if we fluctuate the fields, the phases, we will change the speed of the motor. So this is what a VFD does. It takes your incoming 3-phase, usually in North America 60 hertz, and it changes it. It doesn't have to, but that's the reason why we bought this. It's to change the frequency, and therefore we're going to change the speed of the motor. That's a good thing. So the synchronous speed of a motor is equal to 2 times 60 times by the frequency that the motor is being fed, the electric frequency, 60 hertz, 50 hertz, 40 hertz, whatever, divided by the number of poles the motor has. Let's look at that. So here we have a 2-pole motor. This is what we've been speaking about. And the reason why we call it a two-pole motor is because there are 2 windings per phase. So here we've got 3 phases. We've got the A phase, the B phase, and the C phase. And remember when we looked at each one of those circuits, there was 2 magnets or 2 windings per each of those circuits. So this is a 2-pole motor. There are 2 windings per phase. And in this case, 120 times by the phase that we're feeding this, 60 hertz, divided by the number of poles is 2. So this is a 3,600 RPM synchronous speed motor. Now we never get that out of a motor. We never get the synchronous speed out of an induction motor. What we get is something less. There's always some slip involved. And usually it's in that range of 3450 RPM. It could be 3555, 3545. It's somewhere in that range. And if we want to vary the speed of this motor, we just have to vary the frequency. Let's look at a 4-pole motor. Now, why do we call this a 4-pole motor? Well, there are 4 windings per phase. So we still have the A phase, the B phase, and the C phase, but this time A shows up 4 times, B shows up 4 times, and C shows up 4 times. There are 2 separate circuits, and every circuit has 2 windings, two of those solenoids. So therefore, we have 4 windings per phase, and therefore that's a 4-pole motor. So synchronous speed is 120 times by whatever frequency you are feeding it, in this case 60 hertz, divided by the number of poles, which is 4. And therefore the speed of the motor synchronous is 1800 RPM. Actual would probably be in that 1750 to 1745 to 1755, somewhere in that region. And again, to change the speed here, we would change the frequency. Now, Adrian, what's the difference here? Obviously, there's some speed differences, but what else would be different between the 4-pole motor and the 2-pole motor?
Well, the size of the motor is going to change for sure, because with the 4-pole motor, you have more windings. The other thing that's going to change is your torque available. So we'll look at an equation a little bit later on that relates horsepower to torque and speed. But the horsepower and torque, if you reduce the speed, you're going to get more torque out of the same horsepower, and it's a proportional relationship.
Right. Okay. We'll talk about that in a few seconds here. So there's tables out there. Obviously, I'm just going to go through a couple of them here, but these are the standard synchronous speeds and actual speeds, roughly, that you'll get out of a motor at varying poles: 2-pole, 4-pole, 6-pole, whatever, and it keeps going on. So the more poles, the slower the synchronous and the actual speed. Here's just a quick example just to illustrate that. Adrian did mention that as we go slower, more poles, the bigger the motor. So over on the left-hand side is a 60 horsepower submersible pump. It's a 2-pole. That means it's screaming. It's going at 3450 or thereabouts RPM, and it's quite slender. On the right side, we've got a smaller motor. We've actually got a 50 horsepower motor, but it's 4-pole. It's got those extra windings, and it's quite a bit larger. So it's a little bit counterintuitive that a faster motor is going to be smaller, but definitely that is the case. Obviously, weigh a lot less as well. So from theory to application now, hopefully that gave us some background information. Why do we want to vary the speed of a pump or many other pieces of equipment? But let's talk about pumps, obviously. As we spin a pump faster or rotate a pump faster or add the more piston strokes, we're going to move more fluid. And that's usually the reason why we want to change the speed of a pump. We want to move more fluid. Here, positive displacement pump, we go from 1550 RPM, moving a certain amount of flow rate at the bottom, all the way up to 1750 RPM. We're going to be moving more fluid, everything being constant. With a centrifugal pump, this is just a generic centrifugal pump curve at 1550 RPM. If this was a 4-pole motor, 1800 synchronous speed or about 1750 RPM actual speed. If we wanted to run this pump at 1550 RPM, we'd have to feed it with about 57 hertz, and we should receive a duty point of that blue spot. If we do want to increase the flow, and obviously then the head, because we're always running against that system curve, then we'll run the pump at 1650. In order to do that, we'd have to run at about 57 hertz, and we'd increase the flow, also the head. And finally, at 60 hertz, we're running full out, 1750 RPM, 4-pole motor. We would, again, move out more and more flow. Warning. Now, this has caught me a couple of times. Chris, I think you had to help me out a couple of times on a couple of jobs where I did not heed this warning. You had to go to a very special place.
We all have our weaknesses, Steph. We all have our weaknesses.
I was very young at the time. This is so crucial. And if you miss this, you will pay for a while. Motor horsepower available is equal to the VFD frequency, or whatever the frequency is we were feeding the motor, divided by 60 times by the nameplate horsepower. And right here, I will let Adrian take this away. Adrian?
Yeah, so as Stefan said, when we're running at 100% speed or 60 hertz, we get the full nameplate horsepower from the motor, 10 horsepower in this case. If we're sizing this pump at a lower speed, lower than 60 hertz, we have to make sure that we derate it. So say that we're sizing the pump to run at 50% speed or 30 hertz. Can anybody guess what horsepower we're going to have available from the motor to turn that shaft?
So we're halving the speed, okay.
And this is for one of those gift cards, just to encourage some feedback there. Chris, are you seeing anything?
Yeah, we're certainly getting some answers in. And looks like the consensus is 5 horsepower available.
That's exactly right. So with the VFD, we still have to follow the fundamental relationship that horsepower is equal to torque times the RPM. This is a mechanical relationship, and using a VFD does not change that. So when we're operating from 0 up to 60 hertz, the torque provided by the VFD is going to be constant. And so the horsepower is going to have to vary with the RPM. So half the RPM, half the horsepower.
Right. So keep that in your mind. It's very important. I'll let you explain this, Adrian. You're a lot smarter at this than I am.
So as I said, when we're operating between 0 and 60 hertz, the torque is the constant in this equation. And we see the red line there, the torque is at 100% all the way from 0 up to 60 hertz. And the horsepower is going to increase proportional to your speed. So it's a straight line from 0 up to 100% at 60 hertz. So again, if we're operating at 45 hertz and we have a 10 horsepower motor, we're only going to have 7.5 horsepower available to turn that pump shaft. Once we go above 60 hertz, there are some situations where it's beneficial to overspeed a motor. The horsepower is now the constant in this equation. So when we're operating above 60 hertz, we will always have, from our 10 horse motor, we will always have 10 horsepower available, but the torque available is going to drop off. And again, it's according to that equation. If you flip it around, the torque is going to equal to the horsepower divided by the RPM.
Great. Thanks, Adrian. So let's take a look at an example here. If we have a pump situation, a pump application, and we've decided that this pump needs to run at 1350 RPM to do what we need to do, get the right flow in the head. And we have calculated that we're going to be consuming about 9 horsepower, or that means 9 brake horsepower, whatever's consumed. If we now put a 10 horsepower motor on this application, and it's a 1750 RPM 4-pole, and we incorporate a VFD to run this motor at 77% of its full speed, or 46 hertz, we will achieve that 1350 RPM. Now, can anyone tell me, oh, is this for a car? No, it isn't for a car, so I'll just say it out there right now. We will not achieve, or will not get all that 10 horsepower out, right, Adrian?
That's exactly right. At 77%, you'll get 77% of the horsepower, or 7.7.
And again, it's all due to, whoops, there we go, sorry, I missed that. It's all due to that relationship again of that equation. So what can we do here? What can we do? What would we do if we need to run a pump or a motor at 1350 RPM, and we know we're going to consume 9 brake horsepower? What would be some of our options? Adrian?
Well, one option is just to oversize the motor, to go up to a 15 horsepower motor.
Okay.
So if you're going to run a 15 horsepower motor, 77% of that is well over 9 brake horsepower. So we would have enough torque to turn the shaft at 1350 RPM. That's the expensive option. More cost-effective option would be to change that 1750 motor to an 1150 motor and overspeed it slightly. And if you remember that graph, when we're overspeeding the motor, we still have the full 10 horsepower available from that motor. So 10 is greater than 9 brake horsepower. So if we went with an 1150 RPM motor and ran that at 1350 RPM, we would be okay.
And so therefore we would still maintain that 10 horsepower. Even though now we're running past the 60 hertz, we're overspeeding, the 10 horsepower stays consistent. That's
right. And then your VFD can be sized for 10 horsepower, and your motor is 10 horsepower instead of 15.
Okay. So again, this chart that you spoke about before, we can see that blue line remains constant after the 100% or 60 hertz.
Yep.
Okay. So let's take a look at another example. That was overspeeding in order to achieve a duty point. What happens if we have a wet well? And let's say it's waste product. And we're going to pump from that wet well. As the wet well rises, we're going to pump into a treatment process. So let's get that going. Let me just go over here. And as the wet well rises, the pump turns on. We pump liquid to the treatment process, and then we pump down. The pump stops. The treatment process does not have any more liquid anymore. Then obviously the liquid rises. And what we're getting is a stop-start inflow into, let's say, that treatment plant, which anyone who's looked at treatment plant design knows that treatment plants usually like a nice steady flow. So what we could do here is we could put some kind of a level sensor on the wet well itself. It could be a submersible transducer, or in this case, some kind of a ultrasonic. That's always measuring the level in the wet well. And when that level starts to rise, a signal is sent to a PLC or directly to a VFD, and it tells the pump motor to start speeding up. And therefore, we're pacing the wet well. We're trying to keep that wet well to the same level, and therefore even out our peaks of inflow. And if we do catch up on this, and we find that, hey, we are starting to now bring down the level in the wet well, well, let's slow down the VFD, and therefore, slow down the motor using the VFD, and therefore we're keeping that wet well consistent, and hopefully keeping a more consistent flow that's going to whatever the process is down the line. In this case, it would be a treatment plant. Adrian, you have anything to add in this case?
Yeah, so if we went back to that just on-off control without the level transducer, if we're just operating off of floats and we have an active well, we might also run into issues with cycling the motor too much. I'm sure most people know we're not supposed to turn a motor on and off 20 times an hour. And again, without a soft starter or a VFD, you'll burn out that motor if we have an active pit and a wet well that's not too big, just because the motor will be turning on and off every 5-10 minutes.
Okay, that makes a lot of sense. So it's a process and also equipment lifespan as well. Okay, and let's take a look at a third application here, which is very common. And I know you've worked on several, Adrian. Let's look at a application where we've got a booster system and we've got a wash down area. And we've got some spray wands here. And attached to those spray wands, we've got a header. And part of that header, there may be a huge reservoir here where we may have to fill up a truck. So there's a lot of requirements possibly for water. Unfortunately, this facility, the incoming water supply from the city is just not at high enough pressure to do all the things that they need to do here. So what we would do is we would apply a pump package here. And this pump package would have multiple pumps possibly. In our example, we've got one small pump right here and two larger pumps, all controlled by a control panel and with a, let's say, a VFD on board for all three of those motors. And here is a pressure sensor. So what's going to happen when we start to use some of the fluid here? When one of these wands, kind of light duty, only a small percentage of the total flow is being used, well, we're probably going to get a pressure drop. And this pressure signal is telling us that there's a leak somewhere. Well, I call it a leak. Someone's using liquid. And therefore, we want to maintain a certain pressure. So what's going to happen is this pump, this small pump will probably come on first. And it will try and maintain a certain pressure. And it might eventually do that. Unfortunately, what happens if we start to now increase the flow rates coming from these nozzles or wherever else? Well, that pressure is going to drop even more. So we could have a tuned VFD, so we could start to change the speed of this motor in order to try and keep a constant pressure. Now, again, if this is at the end of a shift and we're really washing down a lot of things, maybe this little jockey pump, as they say, won't be able to keep up. And then it would go offline and we would then bring on one of these larger pumps that could then try and maintain a certain pressure. And again, that VFD is taking signals from the pressure transducer and varying the speed, trying to catch up on itself. There could be a PLC as well in there. And what happens if we really start to open up a lot of the flow? Well, hopefully this has been designed that with this pump running at max or thereabouts a certain speed, it can keep up with the demand. The third pump on the right side would probably be for a redundant situation, or we could turn on an even bigger pump depending on the situation. But the VFDs allow us to try and maintain a certain set point, a design point. Anything to add there, Adrian?
In some positive displacement pump applications, if they don't have VFDs, there's a pressure relief valve or regulating valve. And they, instead of varying the speed of the pump, the regulating valve just dumps the excess flow back to the suction. Okay. And that really wastes quite a bit of energy because we're pumping that water for nothing, just sending it back to the supply tank. And it can also cause problems with overheating the water because the water heats up every time it goes through that pump. So VFDs are certainly, in my mind, a better solution for this application.
Sure. Yeah, you're only operating the pump where it needs to operate. You're not over operating and then bypassing. Yeah,
that's right.
Hey, Steph, we've got a question here that's worth covering now, I think.
Okay.
Go back to that slide with the back one. Yeah. So basically the question is, if for instance the city pressure is enough to maybe fill that drum that you see there on the right hand side of your system, basically, are there any concerns having the low flow that doesn't require any of the booster pumps? So the flow would come from the city through a non-operating pump. And basically, I'm thinking that he's getting at, you know, if there's enough pressure in the city main to fill that drum, therefore doesn't require the pump to start up. Would that be a concern?
I probably would. Adrian, have you seen that? I probably would want a bypass system that would go from the city water supply when we're in a very low flow situation. That bypasses the pumps completely, so we're not pumping through them.
Yeah, I completely agree with that. Especially if it's a positive displacement pump, you don't want to be pushing all that much water right through it without the pump running. So yeah, a bypass valve, probably an automated bypass valve, would be a good alternative.
These are probably, yeah, okay. Yeah, I would say, obviously every case is different, Chris, but yeah, we would obviously take a look at that and make sure that we probably wouldn't want to be pushing liquid through a pump that's not operating.
I agree.
Okay. So centrifugal pumps, variable torque. So let's take a look at a centrifugal pump. When a centrifugal pump starts, it's running very slowly. It's not doing a whole lot of work. There's not a lot of torque being required here. The only work it's really trying to do or have to do is really rotating its own inertia within a fluid. As that pump speeds up, or that impeller speeds up, obviously it's doing more work. There's going to be more torque. So this is a variable torque application, right, Adrian?
Yep, that's correct. And centrifugal pumps follow the affinity laws. So as we do speed up that impeller, the pressure developed by the impeller and also the torque on the shaft are going to increase with the square of the speed. The power required to turn the shaft is going to increase with the cube of the speed. So we can see on these graphs that when we're down operating close to zero, both the torque and the power required to turn that pump shaft are pretty minimal. Because of that, VFDs that are used for variable torque applications can be a little bit lighter duty than VFDs that are used on constant torque applications. The stress is usually at the starting range of the VFD when it's close to 0 hertz, and there's very little required for variable torque loads at near 0 hertz.
Okay. And here's some examples, Adrian.
Yeah, so all of these are good examples of variable torque loads, and they can all be coupled to a VFD, except for the one on the bottom right. Single phase motors cannot be driven by a VFD. If we've got a single phase power supply, what's often done is we feed a special VFD with 120 volt single phase power, and the VFD then converts that to a 208 or 230 volt 3-phase power and connects it to a 208 3-phase motor. So when we're operating with a VFD, even if it has single phase 120 volt input, the motor always has to be 3-phase in order to operate the way that you showed on those previous slides.
I've got a question for you, Adrian. When people throw around the term VFD and inverter, what's the difference? Are they the same? What does that mean?
They're pretty much synonymous, those terms.
Okay. Okay. So here are the positive displacement constant torque relationships. Adrian, I'll let you take that away.
Yeah, so as I said, for variable torque, there's very little starting requirements. With positive displacement pumps, the toughest case is when we're starting the pump up against a pressurized discharge. And when that happens, the pressure and also the torque, even at 0 speed, is right up there at 100%. The power required to start that is going to follow that horsepower equals torque times RPM relationship, where the torque is the constant. So the horsepower is going to go up like a straight line from 0 up to 100%. Now we can see on these graphs both the torque and the horsepower red line for a constant torque VFD are far above the curves for the variable torque loads. So there's a lot more power and torque required to start a constant torque load from a VFD. And because of this, VFDs for positive displacement pumps, they have to have a constant torque, or what's often referred to as a heavy duty amp rating. So whenever you're selecting a VFD for a positive displacement pump, you should always check with the manufacturer that the amp rating that they're giving you on their VFD is the constant torque or heavy duty amp rating, not the variable torque or normal duty rating.
Now, Adrian, this isn't something that you can just buy a standard VFD and you can flip a switch and it turns from one to the other. These are completely different devices.
With the VFD, the same VFD can have both a variable torque and a constant torque rating. So say we have a VFD that's rated for 25 amps for a variable torque load. That same VFD would be rated usually around 22 amps for a constant torque load. Okay. So if you have a 25 horsepower motor, you could probably use that VFD if that motor was on a variable torque centrifugal pump. But if you take that same motor and put it on a positive displacement pump, that VFD is now going to be undersized, and you'll be tripping the overload setting. So you should have to go up to the next size.
Okay, I totally got it. Yeah. And here are just some examples of positive displacement pumps, which we spoke about in the past. Any comments there, Adrian?
No, just these are all often coupled to VFDs.
Okay. So the enclosure, and Adrian will talk about this in a second in more detail, but the actual enclosure, the housing, it's really important to actually correctly select or choose. Obviously, it's got to give protection to the workers and the people around. It's got to give us protection from the environment. Maybe there's water droplets. Maybe it's outside conditions. We've got snow, sleet, rain. Maybe in that spray application, you know, the VFD or the controls could be subject to some direct spray, or oil, foreign matter, dust. It's all going to be the outer portion of the VFD, the protective case, has to be selected as well, and obviously corrosive. So, Adrian, I'll let you take it away with the NEMAs here.
Yeah. So the NEMA rating is a standard way to rate what electric enclosures will protect against. As Stefan said, the NEMA rating of 1 is the lowest rating, and it basically protects you from sticking your fingers on the drive. And 12 gives you a little bit more protection. 3R is what is often used for outside applications, where we're just protecting against rain and ice and sleet. And then the 4 and the 4X, they're used for hose down applications, where we have to make sure that if we're hosing down the VFD, none of that hose directed water gets inside. So NEMA 4 and 4X, they look like they're the best ones. But there's reasons why we might not want to use a 4X rating on a large VFD. Is this a gift card moment, Steph, or is this
Sure.
just...
You're paying for them, right?
Okay.
So yeah.
Yeah. So can anyone out there suggest why we might not want to use a NEMA 4? This is an airtight, pretty much an airtight enclosure on, say, 100 horsepower VFD.
We've got some good answers jumped in before we even finished answering the question, Adrian. We've got some smart people out there. Essentially, yeah, we're getting a combination of a few things, but essentially heat seems to be the big answer.
That is the predominant concern. VFDs inherently, because they're switching at such high frequencies and high power, they do create a lot of heat. And with the NEMA 1 drive, there's open slats and fans inside, and we can just blow that heat away. So there's no issues with having 100 or 200 horsepower NEMA 1 VFD. You just have to have big enough fans inside. For smaller VFDs, maybe say up to about the 20 or 25 amp range, we can put a heat exchanger on the back of the drive of a NEMA 4 drive, and that can get rid of enough heat. But once we get above that 25 amp rating, these heat exchangers don't really get rid of enough heat. And if we're going to be going with something bigger, then what's often done is we take that VFD when we put it inside another enclosure, and the enclosure is going to have that NEMA 4 rating. And then that enclosure has to be usually oversized, so we have a lot of surface area to get rid of the heat, and also have ventilation or even an air conditioning system added. And then inside that enclosure, we have either a NEMA 1 or an open style VFD. Yes. And that can get certainly more costly than just a NEMA 1 VFD for the same size. And the lead time also goes up quite a bit, because these are usually custom enclosures.
So these, what you're showing on the right here, Adrian, you know, up to 50 horsepower or 50 amps, whatever, they're pretty well off the shelf kind of items.
Up to about 25 amps. Yeah.
Okay.
The bottom right one there.
Okay. Okay, so it's some additional hardware here, Adrian. I'll let you take this one away.
Okay, so one of the most popular features we can add on a VFD is a local disconnect. This is great for service people. Instead of having to go back to whatever MCC is feeding this VFD with power to lock it out, they can just turn this handle, put their lock on, and now it's safe to service that motor. There's also protective devices we can add into a VFD circuit. If we have noisy incoming power, either because our utility power is not very clean, or say we have other VFDs or contactors turning on and off all over the place, creating noise in the electrical circuit, then we can add a line reactor in front of the VFD. So this is between the power supply and the VFD. And that will smooth out those spikes in the incoming voltage and the resulting current spikes. So that's to protect the VFD.
Adrian, the same NEMA ratings would occur here that we'd have to be careful about?
Line reactors, some higher end drives come with them built inside, but usually they're external and they would be inside a NEMA enclosure. Yeah,
okay.
This one that you're looking at now, that's an open style one. So you would always have that either inside a control panel or inside its own enclosure.
Got it.
Now, between the VFD and the motor, if we have long lengths of wire, then there can be voltage spikes that are generated that will damage your motor. And so if we're between 100 and 500 feet of wire length, then we might want to add a load reactor. If we're less than 100 feet, then we don't have to worry about it. But once we get up into that 100 to 500 feet range, a load reactor adds some inductance into the circuit that will dampen those spikes that are going to be hitting our motor.
So that protects our motor then?
Yes.
Okay.
The load reactor and everything between the VFD and the motor, they're to protect the motor more than the VFD.
Okay.
If our wire length is greater than 500 feet, but typically between 500 and 1,000 feet, then something called a DVDT filter can be used. And that's still has the same big inductance coils that we have on the load reactor, but it also has some additional electronics to help, further mitigate those voltage spikes that are going to be hitting our motor. And above 1,000 feet, there are other devices, but they're rare and they're expensive, so we're not going to cover those.
Okay.
Another feature that I see in specs a lot for really critical applications is a VFD bypass. So if our motor is turning a really critical load that can never really be shut down for any length of time, a VFD bypass allows us to bypass the VFD and just connect line voltage at 60 hertz to the motor. So when we use this, again, we're only running at 60 hertz. We're not going to be able to run for 45 hertz or 50 hertz. And physically, a VFD bypass is just a set of contactors on a switch. The switch takes the VFD and disconnects it from the incoming power, and then the contactors will connect the motor to the incoming power at 60 hertz.
So it's always good to have in your back pocket if everything fails on the VFD, you can always run your motor at 60 hertz.
Exactly. Yep. Every piece of equipment fails.
And here you got some toys.
Yep. So we often have a number of switches or analog sensors that we connect as inputs to our VFD. We could have a flow switch or a pressure switch to provide safety against running dry or deadheading our pump. The analog instruments, we could have a flow meter or a pressure transmitter or maybe a pH sensor. And these are typically used to govern the speed of the VFD. So we'll ramp the VFD up and down to meet our process requirements. On the output side of the VFD will have a number of outputs to let our customers' PLC or their SCADA system know what's going on with the process. Typical ones are a VFD fault, a run status to confirm that we are running our load, and a feedback signal on what speed the VFD is running the pump at. Or we might want to send back that analog flow meter or pressure transmitter signal back to our customer SCADA system so they can also see what's going on with the process.
Are you finding in the industry over the decade or so you've been in it, or more, I guess, that PLCs are now becoming less and less required because the VFD is doing more and more?
If it's a standalone application and there is there's no SCADA system or multiple variables to control, then yes, a VFD can easily be programmed to maintain one sensor, for instance, a discharge pressure sensor at a certain set points. There's a lot of pre-canned software applications for that, and no PLC is needed. If we're trying to integrate this VFD into a larger control system where maybe we want to satisfy a few different pH sensors with the same load, that's where we would typically need a PLC to help integrate the VFD into the process.
Okay. And here you've got what can go wrong. It's always a good thing to end up with.
Yeah, and I've seen this, most of these things go wrong. The basic selection parameters for a VFD are the current of the motor and the voltage of the motor. So a lot of people, preliminary sizing is often done on horsepower, but when you're actually selecting the VFD, you should look at the current rating of the VFD and also make sure that your voltage matches the actual operating voltage of your motor. Okay. Another thing to consider, we talked about how positive displacement pumps, they have higher requirements for VFDs. So when we're selecting a VFD, we should again check with our supplier that the amp rating they're giving us is the constant torque or the heavy duty amp rating for a positive displacement pump. The NEMA rating, if we select a NEMA 1 VFD and put it in a washdown plant, we're obviously going to have some VFD damage very quickly. So we got to make sure that we match the NEMA rating to the operating environment of that VFD. And the hardware features, again, if our customer is expecting to have a local disconnect and it doesn't, and they have to add their own, they're not going to be happy about that. And for protective features, we got to make sure that if we're operating, say our VFD near other VFDs that are producing a lot of noise, we should have a line reactor on the input. Or if our wire distance from the VFD over to the motor is more than 100 feet, then we're going to have to add either a line reactor or a DVT filter to protect that motor. And last but not least, the inputs and outputs, we have to make sure that our VFD has enough analog or digital inputs to integrate with the process and enough outputs to provide the customer's SCADA system with the information that they require.
Some takeaways here.
Okay, so number one, just the basic sizing criteria. VFDs are sized based on amps and voltage. Number two, we have to make sure that when we're using positive displacement pumps, that we go with the heavy duty or constant torque amp rating on the VFD. And number three, and most importantly, when we're sizing any load, whether it's a positive displacement pump or a centrifugal pump, to operate at less than 60 hertz, we have to derate the motor. And we've seen the equation a number of times. The available horsepower to turn that motor shaft is equal to the frequency we're operating at, maybe 45 hertz, over 60 hertz, times the nameplate listed on the motor.
Right. And this presentation obviously wasn't about any soft starts or across the line, but I'd just like to, finish it up with maybe your thoughts on the differences between VFDs across the line and soft starts, soft stops.
Yeah, well, your slide here shows it very well. A soft starter, it ramps up the speed of the motor and then runs it at 60 hertz and then ramps it down when it's time to shut it off. It cannot vary the speed dynamically to maintain a pressure or a flow the way a VFD can. But there are still places where we would want to use soft starts. Typically, soft starters are less expensive than VFDs, especially when we get into higher horsepowers. You'll see a significant difference there. And say for that wet well pacing application, we don't really need to maintain a constant level or a constant flow. We're just worried about cycling that motor 20 times an hour because the wet well is going up and down. If we added a soft starter there would be no concern with starting and stopping the motor 50 to 100 times an hour because it's not seeing that big inrush. Another almost benefit of soft starters over VFDs is they don't produce the same heat. So a VFD, even if it's running at 60 hertz, it is still producing a lot of heat all the time. The soft starter, it will produce some heat while it's speeding up and while it's slowing down. But while it's running at 60 hertz for most of its life, it's not creating a lot of heat. So if we have a NEMA 4 control panel, we don't have to worry about having a 50 horsepower soft starter inside there. It won't generate a lot of heat.
Okay. Okay, that's good. That kind of rounds out, the other options that are out there. Chris, any questions that have come up?
Here's a couple we can cover for sure. How maximum percentage of overspeed allowed? I guess that's an Adrian question, but I've always said 90 hertz. Is that a good answer, Adrian, or do you have something different?
It does depend on whether we're talking about a 2-pole or a 4-pole or a 6-pole motor. 2-pole motors, you can go up to 90 hertz probably. I wouldn't want to go much higher than that. If you're going with a 4-pole motor, you can go much higher, even up to 120 hertz. But again, you got to make sure that your load is not going to be consuming more horsepower at that higher speed. So with centrifugal pumps, the horsepower, the brake horsepower required up to turn that shaft, it goes up a lot with speed. So you have to double check that at that higher speed, you're not exceeding the nameplate horsepower of your motor.
Okay. I think the answer is no, but can one VFD control multiple pumps?
The answer is yes. There are VFDs that can do that, but they're not, I don't see them applied very much.
Okay, it's interesting. I didn't know that. That's cool. Can you change the torque of a motor?
No. Well, you can lower the torque of the motor. If you run it above 60 hertz, then the torque available will drop off. But the torque, which you can get by taking the nameplate horsepower and dividing it by the speed, and then there's a constant, I think, 52 something. The torque is the torque, and you're not going to get more than that. And it's fixed to the number of windings or the size of the windings that are creating that magnetic current that Stefan was talking about in the earlier slides.
Now, just one little point there, though. We're all up to this point, we've been just talking about 3-phase induction motors, right? And that's what we deal with pretty well every day. Could there not be some other types of motors out there, maybe that these relationships are slightly different, Adrian?
Well, we're never going to violate that horsepower equals torque times RPM relationship. That has nothing to do with motor design or anything electrical. It's a mechanical relationship.
Okay.
So, I mean, we might get better efficiencies out of other types of motors, but I think about 95% of the world's motors are induction motors just because they're so cost effective and they run very well.
Okay.
We've just got time for one more here. Can a VFD be used to protect the motors where there is a voltage imbalance between phases? It's an interesting one.
I have not heard of that being used. I know VFDs, if you mean protected by shutting it off, then yes. The VFD will monitor the 3-phase voltages, and if they become imbalanced, it will shut off the motor. But it cannot fix the problem. Yeah,
I was going to say it can't fix an unbalanced phase, but it could shut down the equipment to protect it.
Yes, yeah, it would be shutdown protection, not a corrective feature.
Okay, and there's a few others. There's a few very specific ones. We will certainly, those that didn't get answered, we will go through these, and there's a few very specific questions that we'll be in touch directly with for the answers for sure.
Well, thanks a lot, Adrian. You brought a lot of expertise to the table here, and we really appreciate it. And Chris, thank you. And thanks to everyone, wherever you are, for attending. Again, we will be sending an email out in the next day or so with a link to our YouTube page with all our videos and many of them for the webinars we've done and other products that we represent. And we're pretty excited about next week, Chris, and 2 weeks time. We've got a couple of things up our sleeves here. Troubleshooting pumps in the field, June 25th, 2020. And hopefully you can join us, and we'll be sending out the invites. And with that, again, thank you, and enjoy the rest of the day, and see you in 2 weeks.
Thank you. See you later.
Thanks, Steph.
Thank you.